Alright, so I'm going to go through a proof of the fact of the statement that the square root of 3 is irrational. So I've done an earlier video where I went through the irrationality of the square root of 2. So the square root of 3, it follows a kind of similar proof. However, there is a slight variation in part of the process involved. So let's begin. So like with the square root of 2, the square root of, we proved that using a method of contradiction. We're going to do the same for this proof. So suppose, I guess for a contradiction, that the square root of 3 is rational. So if it were a rational number, then we could say root 3 is the quotient, or this quotient here, where a and b are both integers. And you should be able to write this in fully simplified form. So another way to say that is the greatest common divisor of a and b is 1. So say if you have a is 4, b is 2, the other way around, say a is 2, b is 4, you could simplify that, and that just simplifies to a half. And we just want, this expression here in fully simplified form. So that is the greatest common divisor of a and b is 1. In other words, a and b are relatively prime or co-prime. So we have a and b integers here and this fact. So we have these conditions. So let's proceed with the proof. So let's play around with this expression. Multiply both sides by b. We're allowed to do that. And let's square both sides. So taking the square of both sides, we get that 3b squared is a squared. Okay. So from this expression, I'm going to use this as a kind of anchor for a few of the remarks I'm going to write down. So we're going to break this proof up into a couple cases where we look at the values for b, and we say, b is either even or odd. So we look at the case where b is even, and then conclude something about the value of a. Same with if b is odd, make some conclusion about what is a, depending on whether b is odd or even. And then we look at the possible contradictions in those cases. So let's go through with it. So let's go through the first case. Say if b is even, we want to kind of get into this form here to be able to draw something from the evenness of b. So if b is even, then it's true that the square of b for b even is also even. Right? So I guess this requires a couple more steps, but we'll avoid this for now. Just believe me when I say that the square of b is even if b is even. So, this here is even. Well, we could multiply this by 3b squared, and that's going to result in an even value as well. Right? Say, as an example, you have b is 2, the square of 2 is 4, and then multiply 4 by 3, you get 12. They're all even values, right? So that's just one case. It works in general. So if 3b squared is even, that's our left-hand side here. And if we have an equality, right, the left-hand side must equal the right-hand side. So if we know that the left-hand side is even, then the right-hand side, namely the value of a squared, is also even. So a squared is even as well. Right? So if you have that a squared is even, it's also the case that a must be even as well. So if you follow this chain of implications here, I'll just simplify it by saying that b being even implies that a is even as well, right? So, what are we supposed to do with this fact? Well, if b is even and a is even, well, we have these two values in this expression here being even, and you could kind of see that this is not really possible if you have this assumption here, right? Because if the greatest common divisor between of a and b is 1, and if the values of a and b are both even, well, it means they're both divisible by 2, which is definitely greater than 1. So we know that 2 divides b, and 2 divides a. Right? So in this case, the greatest common divisor of a and b cannot equal 1, right? So we've contradicted this assumption we've made at the beginning, right? So that's no good. Well, it is good for our proof. So I'll just write contradiction. No good. Okay, so we've only exhausted half the values of b so far by looking at the case where b is even. Now we want to look at, and this is where it gets a bit more interesting, we'll look at the case where b is odd. Okay, so let's go through kind of similar thing here. So if b is odd, then let's take the square of b. Well, this value here is going to remain odd, b squared, and then we multiply it by 3 like we did earlier. 3 times the square of b, well, that's going to stay odd as well. And again, that's our left-hand side. We have an equality. So the right-hand side, a squared, must be odd as well. And if a squared is odd, we have that a must be odd as well. So again, following this chain of implications, we have that if b is odd, then a is also odd. Okay, in this case, well, this is just a fact. You might think, I'm not really sure what to do from here. We don't actually have any contradiction, right? Well, at least an obvious contradiction right now. So let's do some extra working. And the way we're going to proceed is by letting, let's say, b to be, well, we know that b is odd, so we could rewrite the value of b as some even value plus 1, right? So this is even if k is an integer and you add 1, it guarantees that b remains odd. So let b equal 2k plus 1, and let's say a equals 2j plus 1, and where j is just another integer, so where k and j are just both just an integer. Right. So we can do this, and well, let's use these expressions that we've written down and substitute it back into this equation here. So I'll just rewrite it. 3b squared equals a squared. So b is 2k plus 1, so we have 2k plus 1 squared equals a squared, which is 2j plus 1 squared. And let's play around. Let's expand this, and we'll get, I guess I'll just do it in one step. You get 4k squared plus 2k plus 2k, so you get plus 4k plus 1. And that would equal, so 4j squared plus 2j plus 2j plus 1, right? And I'll just expand the left-hand side. You get 12k squared plus 12k plus 3 equals 4j squared plus 4j plus 1. And let's simplify this slightly. We could subtract 1 on both sides of this equation, and we'll get 12k squared plus 12k plus 2 equals 4j squared plus 4j. And I notice that if you look at all these terms here, they're all divisible by 2. So I'm just going to go ahead and divide everything by 2. And I'll get 6k squared plus 6k plus 1 equals 2j squared plus 2j. Okay, well, what I'm going to do is a sneaky little trick here, a bit of manipulation of these expressions to make something a bit more clear. So I'm going to rewrite both sides like this. Plus 1. Right. So here, that's just this portion, and then you have the plus 1. And I just took it on the right hand side, I just took a common factor out of 2. So now with these with this expression here, I notice on the right hand side, whatever this value is here, j squared plus j, whatever it is, odd or even, if I'm going to multiply that value by 2, I'm going to result, it's going to result in an even value in the end. So this guarantees that my right hand side is of even value. Right? And on the left hand side, well, with the similar argument, whatever this expression is, multiplying that by 2 guarantees that this portion of the left-hand side remains even. Now, if this is even, right, and I'm going to add 1 to that value, then this whole expression on the left-hand side will be odd. Right? Now, this is strange. Here we have an equality, right? And we have an odd value on the left-hand side and an even value on the right-hand side. There's no way that they could equal, right? So I can say impossible. So we've shown that, well, in the case where b is odd, right, we run into this roadblock here where we get some sort of, strange equality here. So in a sense, it's an impossibility or a kind of contradiction, right? And, well, they're the only two cases where b is even and b is odd. We went through both of them. That exhausts all the values of b. And we show that whatever b is, we're going to run into a wall. Right? So overall, we have a contradiction. So I'll just rewrite. In both cases, in both, I guess, and all, cases, we have a contradiction, or you could say like an impossibility. So that means we can't find a pair of values A and B such that we've satisfied this criterion here. So no such A and B exists. So we've assumed that root 3 is rational, but our assumption must have been wrong. We conclude that root 3 is irrational.